Alright, so we had stated this theorem yesterday, if you remember. So I'll just open that page. We had stated it and gave an idea that why do we need such things. So from the point of view of projection, that is one dimension, looking at a vector which is u minus that. So recall we had v as v minus w plus w, which is similar to projection, and the orthogonal projection is u minus the projection. Alright. So we had looked at this yesterday, and then based on that we wanted to generalize those ideas, and that was the idea that we are trying to generalize, that we are looking at the projection on ui, looking at its linear combination and trying to proceed. Fine. So let's go back to this statement again and have a clarity of things. So first thing we are saying here is that S is an orthonormal set. So it means orthonormal means orthonormal implies ui ej, their dot product is 0 or their inner product is 0 for all I not equal to j, and length of each vector or the norm of each vector is 1 for all I. This is what it means. Fine. Now we are looking at w. W is linear combination of elements of S. Fine. This is what it says here. Then w belongs to this, because u1 belongs, u2 belongs, un belongs, so their scalar multiple belong, therefore their sum belongs. All right. Fine. What is more important is to understand this part, that v minus w is orthogonal. So what we are trying to do is, let's look at geometrically first, that I have a plane here. This plane is generated by Ls of S. So every element here, any u here is of the type summation u comma vi vi. Is that okay? So any combination here. So recall previous that if I had taken this as my standard basis, B as ordered basis as u1 to un, if I had taken this as an ordered basis, then u in this ordered basis, u in this ordered basis looks like u v1 till u, oh I wrote u1 here, alright. So u and ui here, u and u1. So the last will be n here. Fine. So let me correct it myself. Where did I write here? Vi I wrote here. It should be u comma ui ui. Did I write anything else? No. Everywhere I wrote ui. Yeah. Fine. So what we are saying is that if I look at Ls of S, it looks like this. Fine. Every element here is of this type, and I have a vector v which may be in this or which may be outside. If v is inside, then it is a linear combination, and therefore v minus w will be 0. All right. So if v belongs to Ls of S itself, all right, this will imply that v is linear combination of ui's, I is equal to 1 to n. This is what this will imply, because I am looking at linear span. And from what we have understood, or what I have written here in terms of B, the ordered basis, if I look at the inner product of V with u1, alright, V with u1, this gives me summation I is equal to 1 to n alpha I ui u1, which by the definition of inner product, that I can take out scalars and so on, alpha I times ui u1, which will give me alpha 1 itself, alright, because of the condition that I not equal to j, it is 0, and this part, because of orthonormality I will get this part. So this tells me that alpha 1 is this, and therefore v is nothing but I is equal to 1 to n v comma ui itself, and therefore fine, if I look at v minus w, w is also of the same form itself, will be equal to a 0 vector, alright, fine. So the idea is to look at things from that perspective, that I have a subspace here, Ls of S, and V is outside. If V is inside, it is already linear combination. If V is outside, then what I am doing is that from here I am dropping a perpendicular to this plane, alright. Once I have dropped a perpendicular, this is the origin for me, because 0 0 is always in the linear span, the 0 vector is always in the linear span. So given this V, I am getting this vector this, alright. And what is this vector? this vector is your vector W. This is what it says. W is this vector, fine. So, this is my W vector. What is V minus W? So, look at this, this is what V is, and minus W means this. So, from here I am going this way. So, this is my vector V minus W, alright. So, what it says is that V minus W is perpendicular to every element of this, fine. That is important. So, let us define what is perpendicular. We have done it at the time of what is called fundamental spaces associated with matrices. There we had the inner product as dot product. So, we want to define it for the general setup and then proceed, alright. So, let me just define it here. So, definition. So, given any set S as it is here, I can define S perp as all V belonging to V such that inner product of V with U is 0 for all U belonging to S, alright. So, it is collection of all the vectors which are perpendicular to elements of S, alright, fine. So, here if you verify that if V is perpendicular to U1 and if V is perpendicular to U1 and V is perpendicular to U2 both, this will imply that V is perpendicular to alpha 1 U1 plus beta U2 for all alpha beta belonging to whatever scalar you have. Is that okay? And therefore, what we are saying is that when some vector is perpendicular to the basis vectors, it is perpendicular to everything else, fine. So, use this idea to let us prove that part. So, what we are trying to prove here, let us look at it. We say here that this belongs to this, that is by definition itself, because it is a linear combination. I have to prove that V minus W is perpendicular, alright. So, what we will show is that V minus W is perpendicular to all the elements of S. We are not going to prove it for every element of linear span, we will just prove it for every element U1, U2, Un, and therefore, the remark that I just gave here will imply that it will be there for everything. So, let us look at what is the inner product of V minus Wi, W, and what is this inner product. So, this by definition is V comma W minus W comma W. Now, what is V comma W? V comma W is V comma summation I is equal to 1 to N, fine. I wrote it there, V comma Ui, this is the definition, alright, and this is again same thing, or the norm of V square, you can say it is just the norm, whatever it is. So, I am just leaving it for the time being, we will see whether we need it or not. So, this is same as I is equal to 1 to N, V comma Ui whole perp, V comma Ui, fine, which is nothing but I going from 1 to N, norm of or absolute value of Vui whole square. And what is this? Let us look at, go back, I think, no, so anyway, so let me do that also for you. So, this is nothing but norm of W square, and what is norm of W square? So, since I am looking at scalars here, so if I am writing any vector U as summation alpha I Vi, alright, and Vi's are unit vector, Ui's are, or Vi's here, Vi's are orthonormal, and therefore I will get that norm of U square will be equal to summation I is equal to 1 to N mod of alpha I square, and therefore here W was already consisting of these elements. So, it will be equal to norm of V minus Ui whole square I is equal to 1 to N, and therefore they cancel out. So, therefore, this is 0. Is that okay? So, this is what you have to be careful. So, let me go to maybe the previous slide where I had done this. I think we had done this. So, look at here, we had shown that norm of V square is absolute value of V comma Ui whole square, absolute value of that, alright. So, we had already proved it for any element. So, I am just using that idea and nothing else, fine. So, we have shown that V minus Wi, W is perpendicular. So, we have given the proof in the sense that I have done this part I have done this part. Now if I want to prove this part, norm of V square, then what happens is, let's look at norm of V square. So norm of V square is equal to norm of V minus W plus W whole square, which by definition is V minus W, or how should I write V minus W? Let me expand it totally. So let me be careful, otherwise you will do a mistake, plus W, which is same as V minus W plus V minus W plus W comma V minus W plus W. Alright. We just show that this is 0. Alright, this is 0. Therefore, this part is 0 and this is nothing but this is equal to V minus W whole bar. So which will be equal to 0 bar, which will be 0. Alright. So these two cross product terms are 0. So what I'm left out is this thing, which is nothing but norm of V minus W whole square plus norm of W square. So this is what we have, the Pythagoras theorem. This is what we are saying in some sense, that hypotenuse square is equal to the base square plus, so this is the base square and this is the perpendicular square. Alright. So this is just rewriting what is called the Pythagoras theorem. So we have put it in a different framework, that's all, nothing else. Fine. So we have proved this theorem now. So this theorem is proved. Let us try to understand its implication. It has lots and lots of implications. Fine. Let us try to understand this idea again and again. Fine. First thing is that it's talking about perpendicular. So when I'm talking of perpendicular, lot of nice things happens. Alright. So let's go one by one slowly and build up the ideas here. Alright. So let's look at the ideas. So I have a plane here, some plane P, I have a plane. Now this plane is generated by certain spaces. So it is generated by linear span of some vectors u1 to un. Alright, it is generated by this. It is given to me as a special case, it is given that the set u1 to un is an orthonormal set. So this is given to me extra. Till now I have not been able to say that given any plane I can always get such a space, such a set. That I have not yet able to prove. So question is, given any finite dimensional vector space, can we always produce an orthonormal basis? Fine. What we know is that given any finite dimensional vector space, we always have know what we know. Any finite dimensional vector space has a basis. As only we have a basis. What we have is that any linearly independent set can be extended to form a basis. We have any linearly independent set can be extended to form a basis. Alright. So there should be a way to go from here to here. Alright. That I start with one element and keep building, and then I should be able to get the orthonormal basis. This is what one question is, that I should be able to get it. Fine. Another thing is that we are trying to emphasize here is that if there is a vector V inside the set itself, alright, if I have V which is inside LS itself, LS of S, LS of this whatever it is, fine, LS of S itself, then I don't have to do anything, everything is inside and V looks like, so if V belongs to LS of S, then V is nothing but summation V comma ui I going from 1 to n, or which in some sense we are saying that V in the ordered basis is I am just stressing it again and again, which is very important for me. All right, u1 till v comma un, I have this. If not, if v does not belong to the linear span of S, then it is somewhere outside. All right. If it is somewhere outside, then what I do, I drop a perpendicular from here, fine, and I have some origin with me. Linear span always contains an origin, so I get a vector w, fine. Now what is this vector w? This w is summation I going from 1 to n v comma ui, fine. I have not got the whole vector, I have got this. So this vector v that I am looking at, all right, is this vector, all right. This vector is this vector plus this vector, fine. Therefore this vector is this vector plus this. So we are looking at this vector which is v minus w, and so v minus w we are looking at, which is v minus I going from 1 to n v comma ui. So what we see is that these two vectors are perpendicular. So these two are perpendicular, or what we said, orthogonal, fine. So these two vectors are very nice. Now let us look at from the geometry point of view. In our school, what we had learned was that if I want to find, all right, given anything, any geometrical object, so given any point here and a line, fine, similarly a plane here, that if I want to find the nearest point on this line, so given this point P, the nearest point on L is the perpendicular, in the sense that from here I just have to draw a perpendicular, and this will give me Q, which is the, so this P, point P, I think I should have written here P, fine. So this distance PQ is, so length of this is less than equal to, take any point M, then this length is less than equal to length of PM for any M on the line L, all right. So what we are saying is that the nearest point to P on this line is nothing but the orthogonal, all right. Similarly here, if I take any other point here which is M for me, I will get something which will be summation I is equal to 1 to n some alpha I ui, all right. Then this point will not be nearest to V, but this is the point which is nearest, all right. So this is what you have to be careful. So what we are saying is, in another language is, look at this minimum over, so minimum over all, so let me look at, define it nicely, summation length of say u minus v, length of this, such that u belongs to ls of s, look at this, and minimum is over all u, fine. So this is attained, so this minimum which is a number, this is attained for not u, so I am looking at any u here, it is attained for w, which is, so w which is nothing but I is equal to 1 to n v comma ui. The minimum is attained, so the minimum is attained by w. Well, this is very important, that the minimum is attained by w, and why it is attained? Because of what we had proven here, that, or let me write here itself, that norm of, I am looking at v here, so norm of v square is equal to norm of v minus w whole square plus norm of w square. So therefore if I see this, we have already seen that this is equal to this, so we are saying that this is greater than equal to, this is greater than equal to norm of w square. We are saying this as well as this part because of this idea itself, because they are perpendicular. So again understand, when I have a geometrical object, I have an angle, I have perpendicularity, then the smallest distance is nothing but the one which is a perpendicular, and this is what we have got, that this is perpendicular. We would like to use this idea to build up things. So let us now look at some implications of this as far as our fundamental spaces are concerned. So application to fundamental spaces. Application to fundamental subspace of E, which were M cross N. Fine. So I want to solve the system Ax is equal to B, A is M cross N, X is N cross 1, B is M cross 1. Fine. We have already seen when, so already know the requirement for no solution. All right. We already know the requirement for no solution, and what it says is that no solution if and only if B does not belong to column space of A. All right. So this system has no solution if and only B does not belong to the column space of A. This is what we had seen. What we had also seen was, when we were trying to study fundamental spaces, that look at column space of A, the orthogonal of this is nothing but null space of A transpose. And why did we do that? Understand? So look at this part, or which is same thing as saying that look at column space of A is equal to null space of A transpose whole part. Whatever you want to understand, whatever way you want to do, fine. So we had proved this part for us. Recall here that take any x belonging to column space of A. This will imply that x is equal to A times y for some y belonging to Rn. Fine. If I take anything here, z belonging to null space of A transpose, fine. This will imply that I am taking z belonging to null space of A transpose, not the perp. This will imply that A transpose z is 0. Fine. So now let us look at this x and z, what happens to x and z from here. So I want to look at what is x transpose z. X transpose z is ay transpose z, which is y transpose A transpose z, which is y transpose 0, which is 0. All right. So what we are saying is that x and z, they are perpendicular with a standard inner product. Since I am looking at Rn or A of M cross N, we are looking at only a standard inner product. We are proving results for general setup, but when we come to applications, it is only the fundamental spaces Rn or Cn that we are looking at. So what we have shown here is that any element of column space, and any element of the null space, they are perpendicular, and therefore these two are true. Is that okay? Now we are looking at the case when I don't have a solution, because if I have a solution, I know how to solve it. All right. So my case is looking at, as I said in the previous slide also, we want to look at the case when V is above, V does not lie in the linear span. All right. So again we are doing the same thing. So we are assume B does not belong to the column space of A, implies Ax is equal to B has no solution. So aim to find a vector u belonging to column space of A such that u is nearest to B. I cannot get B using columns, but so I want to find the nearest. All right. So what we do, we write B as, so we know that B is in Rn, whatever it is, so B belongs to Rm. We also know that column space of A is perpendicular to this, so column space of A is perpendicular to this, so I can use column space of A and null space of A transpose. I can look at this, I have not yet defined what it is, defined to get whole of Rm. So if you remember your fundamental spaces, I had done that part, this part, I didn't write this direct sum here, this notion, but what I had done was that I wrote Rm as, this is what I had done here, fine. We wrote here column space of A and there was this null space of A transpose which was perpendicular, alright. So this is what I am putting here, Rm I wrote like this, and which is this language is same as this, that they are perpendicular for me, alright. This has other meaning, but it is, since they are perpendicular, so this will imply this part, alright, fine. So what we are saying is that any vector B can be written as sum of this and sum of this. So we can say that there exist U belonging to column space of A, and I am writing V belonging to null space of A transpose, such that our B is equal to U plus V. Is that okay? Now I want to understand this using everything, fine. So this is what is important for me. So let us look at, so I know that B is this, let us multiply by A transpose. What we know is that A transpose of V is 0. So if I multiply by A transpose of B, I get A transpose of U plus A transpose of V, which is same as A transpose of U. And what is U? U belongs to column space of A. So in some sense you can see here that I have been able to get something which is near. So A transpose U is inside column space of A, alright. And this is what we wanted. I wanted something which is inside, fine. So I have got something here. So let us try to rewrite this in terms of what I am trying to say. So theorem, A is M cross N, fine. The system, the nearest solution of the system Ax is equal to B is, or any system this is obtained by looking at the alternate system A transpose Ax is equal to A transpose V. So let me try to rephrase this in some other language. So to do that, I will start with this following definition. All right. So given two vectors x and y belonging to any vector space V and inner product space, I can talk of distance between x and y. So this is the distance between x and y to be equal to length of x minus y, all right. So this is what we have been doing, that if I am taking it Rn or say R3, I have vector 1, 2, 3 and I have vector say 1, 5, 4 P and Q here, fine. Then the distance between P and Q was nothing but the length of the line segment, length of the line segment joining P and Q. So which was same as looking at, so we looked at this minus this, so we looked at P minus Q, looked at the length which was nothing but, so just keep recalling things one after the other, it was 1 minus 1 whole square plus 2 minus 5 square plus 3 minus 4 square, this is what we had, all right. So this is nothing but, look at this part, this is nothing but length of P minus Q for us, because this is the way we define P minus Q. So for us length of P minus Q means just remove the components here, so take their minus. So you are supposed to look at P minus Q is 1 minus 1, then the second component is 2 minus 5, third component is 3 minus 4, we are looking at this, and whose length is nothing but this, all right. So this is what we had learnt in school and this is what we have. So you are defining distance between P and Q as length of P minus Q. So this you can do it for the general setup also. So whenever I have an inner product, I can talk of this. Now what are the properties of a distance that you should have? So properties of distance that you would like to have, distance. So in place of distance, what you use the word, all right, norm. So let me look at norm. So what is a norm? So definition of norm. So, given any inner product, let V be any vector space. Note, I am not saying it is an inner product space, not saying IPS, I am just saying it is a vector space, all right. Then a norm on V is a function from V to non-negative real numbers for us, all right. So, it is a map from V to R plus union 0, all right. So, it is R plus union 0, non-negative means 0 is included, all right, fine. So, the map is, so it should have certain properties. So, generally we write it as this. So, for each U belonging to V, this belongs to R plus union 0, all right. And what we need is that norm of U is 0 if and only if U is 0, we need this part, all right, for us. So, let me just have the right things, otherwise there will be any problems. So, this is the first thing for us, all right. So, 1, 2, norm of alpha x should be equal to mod of alpha into norm of x for all alpha belonging to a scalar, whatever it is, and x belonging to V. 3, what we need is the triangle inequality, that norm of x plus y should be less than or equal to norm of x plus norm of y, all right, the triangle inequality. Equality for all x y belonging to V. This is what we need for a norm, all right. Now, using this norm, we have this definition of distance, which is distance between x and y is nothing but norm of x minus y. Is that okay? So, I will come to this norm afterwards. You can see that there are a lot of norms. You can also, we have already seen that if V is an inner product space, then distance between x y, which is norm of x minus y, is same as x minus y inner product and then a square root of that, all right. So, this we have already seen. This is the example here also that I have in R2, or I looked at R3. In R3 also I have the same thing, but in general there are other norms also, and we will look at them at the end of the lecture on inner product spaces. So, I would like you to see that such things are there. So, let us go back and try to understand that what we are talking about. So, we are talking about there should be a distance. Distance is basically coming from the norm that we are doing here. Once you have norm is nothing but looking at the distance in some sense, or these properties that I have written here. I would like you to see that this is a continuous function, all right. So, this function that I am defining here, all right, the function from V to non-negative real numbers, this is a continuous function, all right. Since this is a continuous function, in any part, in any interval, it will attain its maximum and minimum closed interval, and therefore, when I am trying to look at distance of anything from a convex part which is closed, things will be nice. So, for us linear span we are looking at, which is a plane. So, it is a very nice object. I am looking at, so I have a plane, I have something, I am dropping a perpendicular. So, I will get something which is the minimum distance, and that minimum distance will be a unique point because of Pythagoras theorem, all right. So, I am doing that part. Thank you.